All right, so we just saw we're doing reactions of carboxylic acids right now, and we saw we can transform a carboxylic acid into an ester, and that's based on just having an excess of the alcohol that pushes the reaction in the forward direction. And that was for an intermolecular esterification, so two molecules going to two molecules. This right here would be an intramolecular esterification. So what does that mean? That means that the ester is being formed from an alcohol that is on the same molecule, intramolecular, the same molecule. So this alcohol right here is what is forming that ester. So which side would be favored in this reaction? So if we did the same enthalpy analysis, we're forming the same bonds that we're breaking. We're forming a CO bond, we're breaking a CO bond, we're forming an OH bond, and we are losing an OH bond as well. So enthalpy is equal on both sides. But it turns out that this reaction is favored in the forward sense. It does go forward. It is an exothermic reaction in the forward sense. Why is that? Well, enthalpy is equal, but entropy favors the products. Entropy, what is that again? That's randomness. There's only one reactant on this side, and here we have one molecule there, so we have kind of doubled the amount of molecules, we've doubled the amount of stuff, and more stuff is more randomness. So what we're going to fill in these boxes, blank of each side is equal, the enthalpy of each side is equal, and remember enthalpy is delta H. But the reaction is entropically favored. Delta S is favored. So that kind of finishes off kind of the esterification part of these alcohols. If we want to take of these carboxylic acids, if we want to take a carboxylic acid and form an ester, we can do that both intramolecularly or intermolecularly with an acid catalyst, and we just have to kind of play around with the conditions if it is intermolecular versus intramolecular. What else can we do with carboxylic acids? All right, so thionyl chloride, SOCl2. It's a specialty reagent. Where did we first see SOCl2? The first time we saw SOCl2 was in chapter 9. Essentially, we learned that we could take an alcohol, treat it with SOCl2, thionyl chloride, and it would transform that alcohol into an alkyl halide. So the ROH went to the RCl. So it did that with alcohols. It turns out it does the same thing with carboxylic acids. Thionyl chloride transforms carboxylic acids, RCO2Hs, to acid chlorides, RCOCls. And it does so by a pretty similar mechanism. And when we think about uphill or downhill reactions, if we're going from a carboxylic acid to an acid chloride, is that a downhill reaction? And you kind of have to think about more than just this functional group, right? Usually we're thinking about the organic molecule going downhill in energy, but we have to think about the whole system. Technically, going from a carboxylic acid to an acid chloride is uphill in energy, right? We're going to a more reactive carbonyl derivative. But what we also have to think about is this reagent, thionyl chloride, is a really reactive reagent. It's not very stable itself. That's why it does this. That's why it is able to catalyze this reaction. We're forming more stable things from this thionyl chloride molecule, and the extra stabilization that getting rid of this provides allows for the slight upward energy of the organic molecule. So what else is formed here? The other things that are formed here are SO2, and SO2 is a really stable gas. So I'll put a G here for gas. And we also form HCl in this reaction. And HCl, even though it's a really strong acid, it's still got, the HCl bond isn't super weak. These bonds in dinyl chloride are really weak. So breaking these bonds and forming the bonds of SO2 and HCl do provide an overall downhill reaction despite the acid chloride being uphill compared to that carboxylic acid. So if we only had these things, if we only had the carboxylic acid and the acid chloride, this would be an uphill reaction. But because we also have these accompanying reagents, these accompanying molecules, the system as a whole is going downhill. So how does this reaction work? When I teach it for this first part in chapter 9, I say, oh, well, what's the most electropositive atom? Which atom has the greatest partial positive charge in dinyl chloride? So we look at the periodic table. We say, oh, sulfur is the least electronegative. That's going to have a partial positive. And just like in the Fischer esterification reaction, where we're treating this with a strong acid, this is essentially electron poor, just like a hydrogen in an acid is electron poor. So the same first step's going to happen. This oxygen is going to add to that, and I'm going to show it kind of as a one-step thing, but essentially we have to remember that there are multiple resonance structures of this carboxylic acid, and we're going to show multiple of them in this process. So actually, I'll just show the first bond first. So we're going to form that bond between this oxygen and the sulfur. We'll show this kind of undergoing a similar tetrahedral type intermediate that we show in other places. So that gives us this intermediate here. These electrons come back down, and the best leaving group is this chlorine right there. So that gives us, oh, also forgot that charge. Doing a bad job right now. So we now have the positive charge on that oxygen, but what I was kind of talking about at the beginning is I really wanted to draw the electrons up from the carbonyl onto that oxygen because that kind of helps us understand what happens next. So if we look at that resonance structure, we can understand that there's Cl minus around, and where's the most electropositive position? Well, we have positive there, but that oxygen's pulling all the electrons toward it, so it's not really feeling that much of a positive. That carbon is the most electropositive place, so the negative of the chlorine is going to add to that carbon right there, and essentially form another tetrahedral intermediate. This board is a little bit small. And now this next arrow is going to be pretty busy. So essentially here we're going to have a lot of electrons moving at the same time. So essentially this SO2 needs to form, and that's going to form from this oxygen. This oxygen is going to pull the electrons from this bond and form a double bond to that oxygen, because SO2 is sulfur double bonded to two different oxygens. This sulfur-chlorine bond is going to break. The electrons in that sulfur-chlorine bond are going to be taken by the chlorine, and those are going to grab that hydrogen right there, and the OH bond is going to break and form the pi bond right there. So you can see the CO pi bond's forming right there, the SO pi bond is forming right there, and the HCl bond is forming right there. All of those things happening simultaneously. So that's what SOCl2 does with these carboxylic acids. It's a really important reagent, and I say that On your note packet, it says the reaction is of vital importance because, the reaction is vital because. Well, what did we just make? We just made an acid chloride from a carboxylic acid. And what does that allow us to make? We said we want to be able, at the beginning of the chapter, we said we want to really be able to start with any carboxylic acid derivative and say, oh, we're going to make this one now, we're going to make this one now, we're going to go wherever we want, we can make any carboxylic acid derivative we want. The kind of key, the Swiss Army knife, as we called it previously, of carboxylic acid derivatives is the acid chloride. You can go to any carboxylic acid derivative in a very straightforward manner from that acid chloride. So this reaction is vital because acid chlorides are the most versatile carboxylic acid derivative. If we start with a carboxylic acid and we want to make an anhydride, how are we going to do that? We can make the carboxylic acid into that, and then we can make the anhydride from that. We can go any which way we want to, starting from the acid chloride. So that's why this reaction is so important. Okay, now we're going to talk about amides. Right up here I have, will the reaction below produce the product indicated? So will these reagents form that product as I've shown it right there? So take a minute, pause the video, think about it, come back. If yes, maybe draw the mechanism. If no, think about why. Okay, so we have an amide, we have a carboxylic acid. So things look like they might work, right? We have the most stable carboxylic acid derivative from a less stable carboxylic acid derivative, so we would theoretically be going downhill. But is there another downhill pathway that is maybe a lower activation energy? And yeah, the answer is yes. So we always have to remember acid-base chemistry is the fastest if it is downhill. So if we have a strong acid and a less strong conjugate acid, then the acid-base chemistry is going to happen before the substitution chemistry happens. So why is that going to happen? Well, we have an amine. Amines are weak bases or weak to moderate bases. Carboxylic acids are moderately strong acids. So if we just look at this equilibrium, forming our carboxylate, our NH4 plus, is this a favorable reaction? Well, what's our pKa here? pKa of a carboxylic acid is 5. pKa of quaternary ammonium is around 9. So we went away from the stronger acid, so this was a favored acid-base reaction. So no, the answer is no, we wouldn't form these at all because once we have this carboxylate, we have a lot of electron density right around that carbonyl carbon, so no nucleophiles can add to that position anymore. Further, we don't really have any nucleophilic species really around if our amine is all the ammonium species at this point, because there are no electrons on that nitrogen at this point. So while this reaction is downhill to form the amide, this is also a downhill reaction. Acid-base chemistry is downhill if we're moving away from the stronger acid. That being said, there is a way to make amides directly from carboxylic acids, and again, it takes kind of a specialty reagent, and it's called dicyclohexyl carbodiamide. I'm going to talk about that in a minute. We can't just take a carboxylic acid and treat it directly with an amine to make that carboxylic acid into an amide. We can't do that because this acidic proton will just be removed by the amine instead of forming the nitrogen-carbon bond. So how do we get around that? We use these amide coupling reagents, and what are they good for? Well, they make the RCO2H, the carboxylic acid, and again, it's got that H here that's acidic, into an activated ester. And esters, they lack acidic protons. So that lack acidic protons. So essentially, what happens here is this is dicyclohexyl carbodiamide, DCC, and this species reacts with the carboxylic acid so essentially this oxygen here gets connected to that carbon there. We lose that acidic proton, and then the nitrogen, instead of deprotonating that, is now able to add to the carbon of the carboxylic acid. This is a mechanism that I think is a little bit beyond the scope of this class. I was teaching a bioorganic chemistry class that's kind of a little bit more focused. I'd go into a lot of peptide coupling reagents. But I did put it into your course packet. So we have DCC right here. That is this CYs that I wrote here are cyclohexanes. So DCC, and then you see that the DCC deprotonates the carboxylic acid. Then that's when it is able to add to that, generating this as the activated ester, which then the amine right here is able to add to that. So you can kind of walk through the mechanism yourself there. It'll probably help you kind of understand why things are happening the way they are happening. But that's straight from your textbook, mechanism 22.7. So yeah, but anyway, DCC and other amide coupling reagents turn leaving groups into activated esters, making the OH atom into a good leaving group. Essentially, if we wanted to make an amide directly from that carboxylic acid, what we would do is treat it with DCC and the amine that you wanted to have on there as the amide. Here we just have a methylamine. So just mix those two together with DCC. There you go. At the bottom, I have another example of that where essentially take that carboxylic acid, you treat it with the amine you want, with the dicyclohexyl carbodiamide, and that would form the desired amide there. How else could we do this? Well, we already said that acid chlorides can make any of the carboxylic acid derivatives. So if we started with the carboxylic acid, treat it with thionyl chloride, that would give us our acid chloride, and then we could just treat that acid chloride with the amine that we wanted to form that amide. So multiple ways of making molecules, right? Both ways are used in the real world. So that's why it's important to know that there are more than one way. So yeah, that's everything we need to know about carboxylic acids. We can turn them into the equal energy esters. So esters and carboxylic acids about the same energy level. We can turn them into the more stable amides, but we kind of have to play around with the conditions a little bit using a special reagent. Or if we use a really reactive reagent like thionyl chloride, that will allow us to take the carboxylic acid and turn it into the higher energy acid chloride. So those are all the things that we can do with carboxylic acids.